just in case, there's a faster way of doing the statistics that you have been looking at. Now, it's the ordinary level way, and unless I was asked to do it this way, I would not do it this way. And what I mean by faster is they simplify how you do it. You don't have to be able to use the log tables, that skill of reading that page in the log tables to do with Z-scores. Sometimes in real life they might use it to speed things up, but really, if you want to be as accurate as possible, you'll do it the way that we were doing things in class, like your confidence interval plus or minus 1.96 times the standard error of means or proportions, depending on the type of data that you have. So, as I said, I would not be doing it this way unless they specifically talk about the empirical rule, or they might use the word margin of error. So the empirical rule, I'm going to start off with that. We have maybe a histogram and it creates a normal distribution. And what you normally do is you go to your log tables, they'll talk about Z-scores, and you'll find the percentages here. And if we were talking about maybe what lies one standard deviation either side of the mean, we would go to the log tables and be extremely specific about this. So if this is a Z-score of 0, which means you're on the mean, then this is your 1 and this is your minus 1. How will we get to figure out the percentage of people that lie, either side, one standard deviation either side? And what I would do is, I'm just going to split this down the middle, and I'm going to find this little bit here. So I always do a couple of diagrams, so I'm not going to change just for a video. So I'm going to find out a Z-score of 1 is 84.13%. So all of that is 84.13%. I'm only looking for the bit here from the 0 up, which means if this is 0, there's 50% before it and 50% after it. So I'm going to subtract my 50%, and I end up with 34.13. And then if that's 34.13, that's also 34.13, which is 68.26%. That's exactly what percentage of the population lie within one standard deviation either side of the mean. That's not what they do in ordinary level. At ordinary level, they talk about the empirical rule, and they really do just learn off that 68 approximately. So they go with approx. 68% of the population lie either side of the mean, one standard deviation. Okay. If you were to do 2 standard deviations, so let's say we want to find out all the people that are within the 2 standard deviations now. So I'm not going to go up just as far as 1 this time. I'm going to go up as far as 2. I'm going to get this, because that's how your log tables reads. It goes all the way up as far as whatever Z-score you're looking at. 97.72. I don't want all the way up as far as it. I want from there up. So if you're at 0, there's 50% before, 50% after, which means I'm subtracting 50%. And that gives me 47.72. I'm going to multiply that by 2. (95.44%) is what accurately your chances of falling within 2 standard deviations of the mean. Whereas they do approximately again, and they say approximately 95%. Okay. And then 3 standard deviations. I do the exact same thing all over again. I go to the 3 standard deviations. That's 99.87. I subtract my 50% to get just the bit up as far as, what's to the right of the mean. That gives me 49.87. I'm going to multiply that by 2. Okay, so hold on. Sorry, 99.74%. They don't say that. We would. 99% is what they say. And that's your empirical rule. It's just a rounded off version of what we can actually figure out exactly from the log tables. Margin of error. So I'm going to do this. That's all your empirical rule here. I'm going to turn over the page, do the margin of error. That's your margin of error. It just means that if you're doing a confidence interval and they ask you to do it the ordinary level way with the 1 over root n, then you would get your confidence interval by just going p hat, so your statistic plus or minus, and you wouldn't have that 1.96 times the standard error of proportions. You just have 1 over root n plus or minus 1 over root n, and that's how you create your interval in this situation. Okay, n being the size of your sample. So you can see it's a much straightforward way, faster and definitely more straightforward way of creating your interval. And again, as I said, I would never do that unless specifically asked to. And then the last thing that you might want to just have a look at, and you can ask me some questions on it if you want, is just, it's called the central limit theorem. It's in your statistics chapter. And you don't need to learn off anything to do with it. Just understand the fact that part of it is just saying that really, if you're going to do a survey, you need to have a minimum of 30 people to survey, or whatever you're surveying. You need to have a sample size of minimum 30. And what they're also saying there is, in the central limit theorem, is that if you do a survey and you get loads and loads and loads of samples, okay, so let's say there's 1,000 people in your population and you decide you're going to survey one sample of 50 people, and you go ahead and you survey that sample and you get an X bar from sample 1. So you get the mean of that sample and you write it down. And let's say you just thought, well, maybe I'll get another mean. I'll just randomly survey again. So I'll pick 50 people out of the 1,000 again. So it won't be the same 50 people. You might, I don't know, you might have one or two people who repeat the survey, whatever. But you're going to get 50 people from the 1,000. You're going to survey them. You're going to get, let's say, the mean, whatever question you've asked them. You're going to get the mean of that. And that would be the mean of sample, your sample 2. And you could do that over and over and over again. But what you'd eventually find out is that, maybe the mean of sample 1 was around there and the mean of sample 2 was around there. On a histogram, let's say, or a bar chart or whatever it is that you're plotting it on. And then you'd have maybe the mean of sample 3 might be there, and the mean of sample 4 might be there, and the mean of sample 5 might be there, and 6 might be there, and 7. Because think about it, the mean of each of your samples should be a fair reflection of the actual mean. But the more and more you do it, now you're going to get some of them, like maybe sample 8, the mean is off out here. But the more and more you do it, the more you'll see it'll actually turn into a normal distribution. So the central limit theorem is just talking about that, and how if you get the mean of all of these means, it should be actually pretty close to mu. And that's actually how we work with things in statistics, because we know that, when we do a survey of a sample, it's never going to give me the perfect answer. But if we did it over and over and over again, maybe then I work with that and can actually get something very close to mu. So have a look at the central limit theorem and see what you think.